Good morning, good afternoon, good evening, everyone. Welcome to our webinar on the In-situ enhanced mineralization value proposition as a carbon dioxide removal technique. My name is Naif Al-Gahtani. I am the General Manager of the Carbon Management Technologies Institute at King Abdulaziz City for Science and Technology, CAX, and I will be your host today. We are thrilled to have you all here with us. And I hope you are as excited as we are actually about today's session. Before we get started, we would like to take a moment to go over a few housekeeping items. If you have any questions during the webinar, please type them in the Q&A box. And we will address them during the Q&A session at the end of each presentation. I would like to let you know that we are recording this webinar and the link of the recording will be sent after the session. Today's workshop is designed to discuss the In-situ enhanced mineralization, EM, which is one of the carbon dioxide removal, CDR technologies. The workshop will include a dialogue between various stakeholders that will focus on the value of the enhanced mineralization, along with the benefits, challenges, opportunities, and potential of this technology to boost its role as a solution to address climate change. We have an incredible lined up of speakers who will share with us their insight and expertise on enhanced carbon mineralization. And by the end of the session, we hope we all gained valuable knowledge about this topic. Now I would like to introduce our esteemed panel of guest speakers, each of whom brings a wealth of experience and knowledge to our discussion. First, we have Professor Monica Prasad, who is a professor in geophysics department and the director of the Mines CCUS Innovation Center at Colorado School of Mines. Prof. Prasad will be talking about opportunities and challenges for CO2 mineralization. Next, I would like to welcome also Dr. Mujtaba Saidi. Dr. Mujtaba is a senior CO2 storage lead at the Global CCS Institute, and he will share insight on CO2 in-situ mineralization in basalt and predated formations. Our third speaker is Dr. Zuhair Al-Yusuf. Dr. Zuhair is a reservoir engineer at Saudi Aramco, and he will discuss the in-situ CO2 mineralization in basalt and deep saline aquifers. Following Dr. Zuhair, we will have Dr. Hatem Al-Hazmi, who is Associated Professor at King Abdulaziz City for Science and Technology. Dr. Hatem will provide a valuable perspective on life cycle assessment for in-situ CO2 mineralization, a pathway of sustainability. Without further ado, let's dive into our first presentation, which is an introduction about the MICDR mission. So please join me in welcoming Mr. Faisal Al-Groni. Faisal works at the Sustainability and Climate Change Deputyship at the Ministry of Energy in Saudi Arabia. He is also part-time consultant with the Saudi Energy Efficiency Center, SEEC. His work in the International Climate Initiatives Department in the ministry involved representing the kingdom in several international initiatives, such as Mission Innovation, the Clean Energy Ministerial, and the Global Methane Initiative. In these multilateral international initiatives, he leads work streams related to carbon dioxide removal, clean hydrogen and methane abatement in the oil and gas sector. He is also involved in the Middle East Green Initiative, MGI, by leading the Circular Carbon Economy Regional Collaboration Initiative. Mr. Faisal, over to you.
Thank you, Naif. It's really my pleasure to be in such panel and workshop with such esteemed speakers. And I'll be very happy to shed some light on the importance of enhanced mineralization from different perspectives. Next slide, please. I will first talk about this importance from my capacity as one of the co-leads in the CDR mission under Mission Innovation. And then also we'll talk about enhanced mineralization importance to achieving climate ambitions, particularly to Saudi Arabia. And last but not least, the role that enhanced mineralization could play in different relevant global pledges. Next slide, please. So starting with Mission Innovation, Mission Innovation is an intergovernmental multilateral initiative, and it has different missions, one of which is the CDR, or carbon dioxide removal mission. And this mission was launched in October 2021 in COP26 with the target to achieve 100 million gigatons of CO2 removals by the year 2030. And there are three short-term outcomes in our mission. The first one is to enhance our current understanding of global CDR status. And then also we have the advancement of R&D and innovation related to different CDR technologies. And last but not least, we are hoping that these two outcomes could lead into global demonstration and pilot projects. Next slide, please. So in our mission, we focus on, we have different tracks that focus on different CDR technologies. These include direct air capture and enhanced mineralization, and bikers or biomass and carbon with carbon removal and storage. There is also one cross-cutting track related to life cycle analysis, LCA, and techno-economic analysis, TEA. And the mission is jointly led by Saudi Arabia, Canada, and the United States, with different members, including Australia, Norway, Japan, and others. And of course, we welcome new members to our mission always. Next slide, please. So I've talked about the three main outcomes that we're targeting in our mission, and we've launched different sprints within our mission to achieve these targets. The first one is the mapping initiative that I will slightly shed light on. And then also we have the student prize competition for the advancement of R&D for CDR technologies. And last but not least, we have the CDR launchpad for demonstration scale tests. Next slide, please. And I just want to bring to the audience attention that our next main engagement in mission innovation will be in Brazil next September for SIM and MI Ministerial. Next slide, please. So for the CDR or mapping initiative, we have launched this interactive map that you can find in Mission Innovation website. And what this map offers is some information about different CDR technologies in different parts of the world. These include DAC, enhanced mineralization, as well as bikers. Next, please. And I'll leave it to you, Naif, to talk more about the mapping initiative in your slide. And I just want to talk about the student prize competition. So to advance the R&D in CDR technologies, we've launched this sprint that focuses on MRV, measurement, review, and verification, because we've realized that to promote CDR technologies, we will need to advance as well MRV. And the official name of this competition is Smart CDR, which stands for Students Monitoring and Reporting Technology for Carbon Dioxide Removal. This competition will be officially launched later next month in the Oxford UK Negative Emission Conference. And then it will be open for applications from different students from all over the world, when it will be announced later in February 2025 in Norway. But if you have any questions, or if you have a team of students that are interested to participate in this competition, please feel free to contact me, and I will be happy to share more information with you. Next slide, please. Yeah, and then also we have the CDR Launchpad to promote pilot test projects. And the target of the CDR Launchpad is to have pilot demonstration projects that have the capacity of at least 1,000 tons of CO2 removal per year by the year 2025, which is next year. And of course, more information could be found on Mission Innovation website. Next slide, please. And just for more information about our mission, you may check Mission Innovation website, or you could alternatively check our LinkedIn page. Next slide, please, Naif. Yeah, our LinkedIn page is very active, and we would welcome you to check it out and get in touch with us if you have any question about our mission, CDR, within Mission Innovation. That's about Mission Innovation. And then talking about the prospect of Saudi Arabia, if you go to the next slide, Naif, please. So Saudi Arabia has announced that it will adopt the circular carbon economy approach in 2020 during our presidency for the G20 countries. And we will adopt this framework to achieve net zero by the year 2060. And the idea of the circular carbon economy is to focus on the emission sources, the emissions rather than their sources. So we target to manage the emissions in a circular manner. We have what's called the 4 R's: reduce, reuse, recycle, and remove. And each R focuses on different kind of technologies. When we talk about reduce, we have energy efficiency and renewable energy, for instance. There are different technologies within the reduce and recycle, of course. And then when we talk about remove, we have the different CDR technologies, including the mineralization. So we are aspiring a scale up of the mineralization to help us achieve our climate ambition. Next slide, please. Yeah, and last but not least, when we talk about global pledges, we have the Carbon Management Challenge that was launched last year with the target to achieve 1 gigaton of removal of CO2 from CCUS and CDR. So there are 2 main technologies there, and this target is by the year 2030. We have different countries there, and again, in our hope is that enhanced mineralization can play a role in that global pledge as well. Yeah, and then again, enhanced mineralization has a high potential for storage, but then again, in the context of CDR, we are focusing on other aspects such as the removal and the capture as well. So this is what we're trying to identify through our work, and hopefully discuss through this workshop by identifying or discussing the value proposition for CDR technologies, and then also how we could verify these removals through different MRV measures that companies can apply. That's it from my side. Thank you, Bender. Back to you.
Thank you, Faisal, for the insightful introduction about MyCDR. And I would like to add a topic regarding to the enhanced mineralization CDR. I will talk about the EM resource mapping exercise and our current progress in this area. In this slide, I am showing you the data that we are used to build our resource map. One source of this map is from the survey forms we sent to our country members. They completed the survey. Would like to thank them all, indicating different priority areas for the EM track, including the R&D, scaling EM, techno-economic assessment, life cycle analyze priority, and monitoring, reporting, and verification priority. Another source of data is from the available published information. We collect data from different open resources like academic papers, project website, official government website to track the status of enhanced mineralization project worldwide, including the type of mineralization and the total tonnage of carbon captured per year using this technology. By the way, this is a live document that we are updated eventually as part of the EM technical track. This pie chart illustrates the global status of EM pilots, demonstration, and deployment. Currently, there are 91 pilots, demonstration or deployment worldwide. Of the announced EM project, there are 41 projects with highest number in several countries. These announced EM projects represent over 54, so very high number of announced projects of the global EM CDR pilots. The operational EM project account for 35% of the global EM CDR pilots. Here, the total, like from our screening, the total of storage from the EM project, otherwise announced or operational, it's around 5 million tons of CO2 per year. Now I would like to share with you the survey form that we sent it to our country member. This survey aims to understand the member country activities within the priority areas identified for the enhanced mineralization track, and to identify the available data sets for EM resource mapping exercise. To achieve the EM track and its objectives, a focus on 4 priority areas is required. As mentioned in this survey, it's to meet the MICDR missions goal to enable the CDR technology to achieve a net reduction of 100 million tons of CO2 per year globally by 2030, as Faisal mentioned, and to set the necessary foundation for realizing the potential of enhanced mineralization industries globally. Thank you. With that, I would like to move to our main guest and start with our technical presentation. So please welcome, join me to welcoming Professor Manika Prasad. Dr. Manika Prasad is Professor in Geophysics Department, the Director of the Mines CCUS Innovation Center, and a Co-Director of Center for Rock and Fluid Multiphysics. Her research interests are multidisciplinary research on rock, sediment, and fluid properties, multiphysics, quantitative nano and microscale characterization, flow zone mapping, and non-destructive materials characterization. She recently led a Department of Energy project on CO2 storage and is leading the mines portion of the DOE SMART initiative. Through her teaching and research, she engaged the next generation of industry professionals through her own clear understanding of rock physics and prospective questioning of her student. So with that, Dr. Manika, it's over to you. But let me just share your slide. Just give me 1 second.
In the meantime, I can say hello and thank you very much for inviting me to present at this forum. It is really very interesting, and I've listened with great interest to Dr. Al-Koroni, about the new thrusts in the mission innovation for CDRs. It's really exciting, and also I'm very gratified to see that there is student involvement. So I'm sure it will excite students across the world to say, this is something we really want to do. So very pleased to see what's happening in that field. I thought I will present a little bit on what we do at the Colorado School of Mines, but also what are the opportunities and what are the challenges for carbon dioxide mineralization. So if we can go to the next one, this is just to give you an idea of who we are. We have just graduated a whole bunch of students. You can see one student from Saudi Aramco, Ali Al-Saad, who was a brilliant student. He just graduated and he'll be going back, I think, in June. And then we have a number of new students who are coming in. On the right-hand side, you have the leadership in the group that is with myself leading the group, and then we have Louis Serpa, who's a petroleum engineer, Wei Ping Wong, who's our lab technician, and Athos Nathanael, who's our postdoc. May I have the next one, please? Okay, so How can we optimize? We really want to get this project of having to store and sequester 1 gigaton of carbon dioxide per year. We are still in the infancy because every project we have worldwide is on the order of thousands of tons, not millions of tons. And so we really need to scale up. Either we need to scale up on single projects or we need to scale up on the number of projects, most probably both. And so that's where we stand today. So if you go to the next slide, please. The question we need to ask ourselves is, where can we store? What is the optimization process that we need to do? These are pictures from the Deccan basalt. We've just started a project on mineralization in the Deccan basalt in India and in offshore basalts in Norway. And what the questions we are asking ourselves is, what is the critical element? Is it mineralogy? Is it the fluid reaction? Is it the residence time? Or is it a contact area, the surface area that's available for reaction? Most probably, it's all of the above. But the question then becomes, if we are trying to do in situ mineralization or even on surface mineralization, we need to know how much of the gas has been consumed, how much of the fluid has been consumed, so that we know how far the process is. Have we been successful to mineralize everything? Is there capacity for more? So every formation, every well, every location that we go to needs to have that conversation of optimizing the reactions so that we mineralize faster, efficiently, and permanently. And monitoring and verifying that, yes, indeed, we have mineralized. So that's the challenge that we face today. Can we go to the next one, please? And so the problem still remains age old, and that is, where does the fluid reside? How much do we have? And we've seen that in water research, we've seen that in oil and gas, and now we see it in sequestration. We need to know how much of the fluid we've put in and where is it going. Next slide, please. So if we look at carbon dioxide mineralization, direct capture, direct mineralization of carbon dioxide in the atmosphere, we know that it can alter the minerals, alter the frame, and it can.
Yeah, Dr. Mujtaba is a senior CO2 storage lead with a PhD in reservoir engineering from Herwitwatt University in UK. He specialized in carbon storage and mineralization within subsurface formations, providing reservoir engineering and an advanced analytical and numerical modeling solution for CCUS project. Mujtaba's extensive experience spans various modeling disciplines, including hydrological, thermal, and geochemical modeling, effectively applied in reservoir characterization, development planning, injection, production, optimization, and assessment of storage capacity, injectivity, plume, mitigation path, migration path, contaminant integrity, and operational risk areas. With over a decade of experience, Mujtaba has successfully led major industrial projects globally, covering regions such as the Middle East, United Kingdom, Denmark, Japan, Southeast Asia, India, Canada, and Australia. So Mujtaba, it's over to you.
Thank you very much, Dr. Naif, for such a nice introduction. Hi, everyone. Thank you for attending this webinar on in-situ mineralization. Today in this presentation, I would briefly provide an overview of carbon dioxide in-situ mineralization technology and some of the challenges and opportunities. But before I begin, I would like to thank the King Abdulaziz City for Science and Technology for providing us this excellent opportunity to discuss this fascinating carbon dioxide removal technology. We need more webinars like this to freely share and exchange knowledge on this technology that could hopefully help with its further development and adoption by the industry. Next slide, please. So before jumping to the main talk, I would like to very quickly introduce my company. I'm coming from the Global CCS Institute. We are a nonprofit climate change think tank. Our mission is to accelerate global deployment of CCS. We are a member-driven organization with over 200 members. For more information, I encourage you to visit our website. So without further ado, let's jump into the main discussion. So what is in-situ carbon mineralization? Let me to just briefly define this in-situ carbon mineralization technology first. In-situ carbon mineralization is the process of carbon dioxide reacting with minerals to form carbonate minerals in the subsurface. Through this process, carbon dioxide is dissolved in water, either at the surface or in the wellbore to create the carbonated water. The dissolved carbon dioxide in water reduces the pH of the water and thereby increasing the H+ concentration, forming a weak carbonic acid. The H+ ions thereby can react with calcium and magnesium and iron-bearing silicates such as pyroxene, plagioclase, and olivine, common minerals in basalts and peridotites, releasing divalent cations into the injected fluid. The divalent cations can then react with the carbonate ions in the injected fluid to form carbonate minerals such as calcite and magnesite, thereby permanently locking the carbon dioxide in as minerals in subsurface. Next slide, please. So carbon mineralization technology has received little attention compared to conventional carbon dioxide storage in sedimentary formations. And this is due to various reasons, but one of them is that mineral trapping has been overlooked as a primary trapping mechanisms because the permanence of carbon dioxide through carbon dioxide storage through these trapping mechanisms has been perceived as slow and insignificant in sedimentary formations. The figure on the left side in this slide shows the carbon dioxide trapping mechanisms in sedimentary rocks versus time, while also the figure on the right shows the trapping mechanisms during in-situ carbon mineralization technology in mafic and ultramafic rocks when injecting carbonated water. Comparing the two, it is evident that under suitable subsurface conditions, mineral trapping is effective and fast trapping mechanisms during carbonated water injection. A good example of successful application of this technology and rapid mineralization is CarbFix projects. The projects operating in Iceland is currently the only commercial scale application of in-situ mineralization technology. During the CarbFix pilot test in 2012, it was reported that over 95% of the injected carbon dioxide had mineralized within 2 years. And so far, they have stored over 17,000 tons of carbon dioxide successfully. Next slide, please. Mafic and ultramafic rocks are abundant worldwide, as shown in the figure in this slide, which could make the technology an appealing and attractive option for countries or regions without suitable sedimentary formations for carbon dioxide storage, or where the sedimentary basins are too shallow or don't have a perfect seal to permanently store the injected carbon dioxide. The figure also on this slide also shows the carbon dioxide storage capacity in mafic and ultramafic rocks. However, it should be noted that the values reported in this slide and in some of other publications, these are optimistic values obtained by simple 1D calculations. These values can only serve as a guideline to gain a basic understanding of how much carbon dioxide removal opportunity this technology can potentially offer worldwide. When it comes to more detailed and site-specific assessment, it becomes clear that there is a lack of consistent and reliable methodology for resource estimation and storage site characterization for utilizing this technology, as opposed to conventional CCS. For example, for CCS, we have multiple workflows published by DOE, EPA, and other well-known organizations around the world on basin and site scale assessment, initial characterization, detailed characterization, up to the start of operation and injection. So we need such a standard workflows for in-situ mineralization technology. So there is a room for improvement in this space. Next slide, please. There are several key operational factors that can influence success, scale, and cost of the technology. These key considerations should be carefully evaluated before implementation of the technology. In here, I would briefly discuss only a few of these factors. The first one is the water consumption. Water consumption is a crucial factor to consider because the process requires dissolving carbon dioxide in water to facilitate the reactions. And since the solubility of carbon dioxide in water is relatively low, we need a significant amount of water. Typically, we are talking between 25 to 45 tons of water is required to dissolve 1 ton of carbon dioxide. The good news is that water is not consumed during the process, so it can be recycled. However, recycling is also challenging, and it comes with its own operational considerations. I should mention that Carfix recently has started using seawater in their sea stone projects. If successful, it can unlock the true potential of the technology, as using fresh water is not feasible in some parts of the world. Next slide, please. So the second concern is, or key consideration is carbon dioxide injection rate, or the scale of storage. Based on the solubility data presented earlier, under the same operational conditions, the injection rate of carbon dioxide per well via carbonated brine injection is expected to be approximately 25 to 45 times less compared to plain carbon dioxide injection. This lower injection rate is solely because of the injected carbon dioxide is dissolved in water, and its solubility in water is relatively low. So the main portion of the pore space would be occupied by water. This significantly impacts the scale and cost of the technology. For example, for a Sleipner, the injection rate of carbon dioxide is around 1 megaton per annum using one well, while for Carfix 2, it was around 0.01 megaton per annum using one well. So it's 100 times less. This means to get to the larger scale, an economic, like an industrial scale, a network of injection wells are required, although wells can be shallow. So shallow wells make the drilling easier and cheaper, but the need for a network of wells adds to the cost and require a network of surface injection facilities and transportation infrastructure, which could impact the OPEX and CAPEX. Therefore, there is another research opportunity in here to look at actually technical and economical viability of larger scale application of the technology. The third consideration is the risk of carbon dioxide leakage. So if you go to the previous slide, please. Thanks. The injection fluid in case of in-situ mineralization is carbonated water. Therefore, carbonated water injections offer a key advantage over plain carbon dioxide injection in terms of reducing the risk of carbon dioxide leakage. When injecting carbonated water, the dissolved carbon dioxide is not present in a free gas phase, thereby minimizing the possibility of upward carbon dioxide migration. So the need for a perfect topseal may not be required for this technology. This makes the technology an attractive option for regions where the sedimentary basins don't have a perfect seal for permanent storage of carbon dioxide. You may have noticed that I was very careful with my wording earlier. For example, I mentioned that the technology reduces the risk or minimizes the possibility of upward migration. And the reason I'm being careful here is that if the carbonated water flows toward upper zones and experiencing a pressure drop, such as when there is an unwanted fracture toward upper formation, the pressure drop can cause carbon dioxide can emerge from the solutions and form a free gas phase. So to avoid this risk, comprehensive fracture characterization and assessment of fracture initiation pressure and propagation pressures are essential. Next slide, please. One main concern is in the injectivity. Injectivity is a direct function of the viscosity of the injected fluid and the thickness and permeability of the reservoir interval. The permeability of basaltic rocks are highly variable depending on the cooling rate of basaltic lava flow, the number of character interflow zones, and their thickness of the flow. But all in all, what is clear is that fractures play a crucial role in fluid flow and injectivity in basaltic flows and fracture prototypes, with matrix offering low permeability and fractures serving as conduit for flow. So therefore, it is very important to do a comprehensive characterizations of fractures and faults if present to evaluate the injectivity. And to optimize the injectivity, and it's very important to have the wells intersected the primary fracture planes and perforated at fracture intervals. Next slide, please. However, we should not forget about the role of geochemical reactions on injectivity. For example, it is expected that in the near wellbore regions, the solution occurs strongly, hence aiding the injectivity. But on the other hand, we have precipitation mainly occurring in the main reservoir body, eventually leading to clogging of fractures. So it should be noted that clogging eventually affects the injectivity, potentially requiring new well drilling. However, the time when this injectivity loss occurs depends mainly on geochemical reactions, fracture network connectivity and extent, and carbonated brine injection rate, ionic compositions, and pH levels. So there are multiple factors, hence it requires a careful assessment. On the same note, for the case of in-situ mineralization in prototypes, we should not forget the potential role of reaction-driven cracking. Reaction-driven cracking is known to be the mechanisms leading to 100% completion of geologically prototype carbonation. Reaction-driven cracking potentially enhances the injectivity and creates new flow pathways for the injected fluid. It can also help creating new surface areas for reactions. So reaction-driven cracking, if occurs, could enhance the injectivity and maybe even sustain the injectivity in peridotite formation, but it comes with its own operational challenges that I would explain in the next slide. Next slide, please. So a few years ago, Zhang et al. Studied the effect of confinement on the coupling between stress generation, reaction-induced fracturing, and porosity evolution during the hydration of magnesium oxide into brucite. Samples of magnesium oxide ceramics were hydrated at multiple temperature, confining pressure, differential stress, and pore fluid in a triaxial cell. And as you can see in this video, they did a smart, experiment and look at all of the changes, in-situ changes, by using an X-ray macrotomographic imaging at every 5-minute intervals. So they observed that when the effective mean stress is less than 30 megapascal, the fraction of magnesium oxide replaced by brucite is a function of time. And after a slow start, the replacement rate picks up, as you can see again in the video, with intense fracturing. And the porosity increases resulting from the reaction-induced fracture is pulse-like. So it goes slow and then it goes fast. On the other hand, they observed that if the effective mean stress is higher than 30 megapascal, no reaction-driven cracking would occur. So this shows that reaction-driven cracking also depends on effective mean stress applied on the rock. So if it occurs for peridotite, if this reaction-driven cracking that we are seeing in here would occur for peridotite, it can enhance the injectivity, it can enhance the reaction surface areas and therefore reaction rate, but at the same time, it may lead to surface uplift, fracture formation and propagation, maybe toward upper formation, proposing leakage risk and maybe even contamination of underground source of drinking waters. And overall, it complicates the modeling process of this technology. So there is a huge R&D opportunity in this space to better understand what is the impact of reaction-driven cracking. Next slide, please. I think MMV is very important, monitoring, measurement, and verifications. For the conventional CCS in sedimentary formations, we are heavily relying on conducting time-lapse 3D seismic surveys, also known as 4D seismic surveys. They can detect the carbon dioxide plume and whereabouts of the carbon dioxide. However, for in-situ carbon mineralization, since the injected carbon dioxide is not in the free gas phase, 3D seismic monitoring techniques relying on detecting the carbon dioxide plume or vertical seismic profiling are not applicable to determine the whereabouts of the dissolved carbon dioxide phase or whether it is mineralized and safely contained in the storage complex. So for this technique or this technology, we are relying on gas detectors, temperature and pressure sensors, reservoir modeling, monitoring seismic events, and tracer tests. And for measurements and verifications, we are also relying on tracer tests, regular fluid sampling, and drill core samples. So once mineralization is proven via an adequate techniques, long-term monitoring is not required, which is a great advantage of this technology as opposed to carbon dioxide storage in sedimentary formations. Because in that case, we need to actually monitor the carbon dioxide plume post-injection period. Next slide, please. So this is my last slide on the key considerations. The area of review is defined as the area surrounding the injection site where the underground source of drinking water, or USDWs, may be at risk of contamination through wells, fractures, or faults, or any other pathways that penetrate an injection zone. The area of review is determined by identifying critical pressure that can reverse the flow direction between the lowermost underground source of drinking water and the injection zone penetrate, potentially causing fluid flow from the injection zone to the drinking water aquifers. So in the case of carbonated brine injection or in-situ mineralization, even though that carbon dioxide is not in the free gas phase, the elevated formation pressure induced by injection may lead to the flow of non-potable water from the injection zone toward the upper formations and therefore underground source of drinking water, if there is any. So it may also impact drinking water quality by changing the pH, salinity, and causing leaching of metals. The same concerns may apply for agriculture source of water, depending on the country and the regulatory framework of the region. So to avoid these risks and such a reverse flow situation, it is essential to predict the area of review, define the MMV plan for the whole area of review, and not only around the immediate vicinity of the injection well, but also across the whole area of review. This would ensure the potential impacts on drinking and agricultural water sources are monitored comprehensively and effectively managed. And we use numerical simulation for that can be calibrated, during the operation as well. Next slide, please. So this is my last slide. I'm cautious that I've already exceeded my presentation times by a few minutes. So just all in all, this technology is a very promising and interesting technology. It can be an alternative technology for CCS in areas where there are no suitable sedimentary basins available for conventional CCS, or where the basins lack a proper seal. But I should mention that there are still several aspects that requires careful assessment to better assess the feasibility, technical feasibility, and economic viability of the technology. And lastly, conducting pilot tests and publishing the results are crucial for gaining a better understanding of this technology in basalts and prototypes. So next slide. Thank you for your attention. And for more detailed information about this technology and other key consideration, feel free to reach me via emails or LinkedIn. Thank you.
Thank you. Thank you very much, Mujtaba, for your great presentation. And now we will have 3 to 5 minutes for any questions to Dr. Mujtaba regarding to this topic. And then we're going to go back to Dr. Manika just to finish.
That's great. Yeah, that's great.
Welcome back, Dr. Manika. I got a question actually regarding to the injectivity, if you allow me to ask Dr. Mujtaba. How different basalt compositions affect the injectivity and subsequent mineralization of CO2?
So we need to do actually proper characterization of the site and doing the simulations to understand the impacts of mineralogy on the injectivity. It's not something that we can, say without knowing the knowledge of the subsurface. The easiest way to say is that if you have more reactive minerals, you would have more dissolution near the wellbore, and hopefully the reactions would be strong, reaction rates would be stronger. But all in all, injectivity mainly is a function of having fractures, a good fracture network in basalt. Basalt by itself, the matrix doesn't have a good permeability. So if you don't have a good fracture network, the injectivity would be very poor. Or if the fracture network is there, but is naturally sealed by carbonation process, then the injectivity would still be poor and may require the stimulation techniques.
Okay. We're going to wait for any question. Otherwise, we're going to start, go back actually to Dr. Manika.
All right, sure.
Yeah, just 1 second. Thank you very much, Dr. Mujtaba. And we're going to now go back to Dr. Manika. So welcome back, Doctor. And we're going to start from where we lost you, I think here.
Yes, thank you very much. And Dr. Mujtaba, thank you for jumping in. I'm traveling, I'm in China, so suddenly I think this is evening time. And I think at the hotel, everyone's streaming, so they threw me out of the server. Anyway, so what we were talking about, and I think I was very glad to hear Dr. Mujtaba talking about mineralization, because the whole thing is that we have mineralization. We know mineralization is happening, but we have a very inadequate model right now to map and differentiate between fluid effects. We need to quantify fluids and mineral effects. Both of these affect our indirect signatures. And it can be an opportunity or it can be a problem. It all depends on how much prior information we have. It will also affect fluid mobility. So if we start reacting, if we start changing permeability, we start mineralizing, we really need to understand where exactly is the mineralization taking place. Are we mineralizing at the pore boundaries? In which case, we would reduce porosity. Or we are reacting at the interfaces, and in that case, we might be reducing permeability quite a bit. If we are dissolving at the interfaces, we would be affecting the geomechanics of the formation, and that might lead to large problems. And so we have a real lack of information, a lack of systematic studies that tell us how the process takes place and how to optimize. Ideally, what we want to do is be able to combine reservoir simulations. So we have THMC models, that is thermal, hydrologic, mechanical, chemical models, and combine them with geophysical and flow simulations so that we can have a better idea of how to map the reaction front and differentiate it from the fluid front. If you go to the next slide, please. Let's look at some rock-fluid interactions. So these are the types of reactions we can expect to find. We have here, in this case, these are feldspars and quartz. The pink is a feldspar. The gray is a quartz. And we can see that there is large-scale alteration and cracking of the mineral in the case of a feldspar, but not in the case of quartz. The matrix is pretty much the red stuff. So the red part is what's reacting. And in this case, in our case, we would have carbonates going in. The red would be the pore space, and the reactions would be taking place either at the grain boundaries, at the contacts, at what is carrying the load, what is giving me the geomechanical strength of the formation, or it would be happening at the boundaries of where the pore space is, where you have maximum contact and exchange with the pore fluid. You go to the next slide, please. And this can change depending on the type of rock I have. In this case, there is an andesitic formation, and we see that there is leaching out of the mineral parts into the matrix. And so we have and there is large scale pitting of the rock. So the reactions that are happening are twofold. They are pitting the inside of the rock, of the mineral, and they're leaching out the chemicals and then depositing them in the pore space. And so all of these will give me a change in the permeability, in the flow space, in the storage capacity, and in the strength of the material. Next slide, please. If we have cements, and this can happen also in a sandstone formation. This is a very typical sandstone. On the whitish colored rock is a feldspar, and you see on the bottom it is completely hollowed out through reactions. On the right-hand side, we have a quartz, but the cement between the two is the part which I'm interested in, because if we are attacking the cement, then we will grossly compromise mechanical stiffness, and we will compromise the geophysical signatures. And so these types of reactions are something we really want to understand and map and be able to model, so that we can create a 4D geophysical model, we can create a 4D reservoir simulation that tells us what to expect and when the formation has completely reacted. And so we should plug and abandon and move on to the next one. Ideally, we do not want to have any fluid that is left over, that is unreacted, because it has the capacity to then leak. And so our requirements for monitoring after we have injected become smaller if we can show that the entire amount of fluid that we put in has reacted. And so we have only mineral space. We do not have any more carbon dioxide that's left to react. At the moment, we do not know how long it will take. We have early data that came in from Benson and et al. In 2001, 2010, that said this is going to be a very long process. Mineralization doesn't happen very fast. And then about 10 years ago, people started saying, no, the results have shown that this happens on a lab scale within weeks or months. That time scale needs to be fixed. We go to the next one, please. Even in a brine formation, this is brine, and in a sandstone with carbon dioxide in, we see that we can start getting salt precipitation. And so if we are putting salt water, for example, I'm very curious to see the results after a few years from Iceland, because if we're using salt water, we have 50,000 ppm at least salinity. We mix that with brine, we inject that in. Now we start seeing possibly mixture with existing brines, and we might see a salt precipitation coming out. Or we might have an enhanced effect of even more dissolution. The problem is, the challenge is, we really don't know. And that's the part which we are trying to fix, is to say, where does the reaction take place? How fast does it happen? What promotes it? We know that the temperature and pressure will promote reactions, but can we also enhance reactions with increasing surface area? Or is the surface area of exposure to the fluid a smaller effect, and the chemistry is a larger effect? So those are some of the questions that we're trying to answer. And along the way, for the project that we've just started with the Norwegian and the Indian basalts, is to say, how should we inject such that we can get the fluid out away from the borehole before it starts to react and clog up the pore space? And so we need to optimize between reaction rate and mineralization rate and the injection speeds and the volume and the pressure of injection, so that we break whatever's forming initially, get the fluid out, and then let it react. Can we go to the next one, please? We know that the velocities in basalts are pretty high. So these are seismic. Usually we use 4D seismic. In our case, 4D seismic might not work, which means that we might need to go into electromagnetic mapping. So controlled source EM mapping, or more shallower techniques, or some other ways of doing tracers, or some sort of a carrier that gives us a better geophysical signature that allows us to map the fluids. Next slide, please. If you look at the alteration in basalts, it's really a fast process. This is from a recent paper, not so recent, 2006, and the reaction with the basalt and carbon dioxide gives rise to a coat of calcite everywhere. And this is, in a way, good, because the reaction takes place within a few weeks, 32 weeks in this case. It can also be bad news, because now it's clogging up everything. And so if we are clogging up the pore space, and if you look over here, you have the green part on the left-hand side, that's the calcite that's coating the entire basalt specimen. On the right-hand side, in a thin section, in an SEM image, you see that the white coating is the calcite that is coming in as a film over everything. The question really remains is, A, what did it react with? Which mineral was reacted? Is it a uniform reaction? B, how stable is this reaction going to be? And so the reactions will be dependent on later on. Let's say we finished all the reactions and now it's flooded with brine. Do we start to dissolve again? Next slide, please. And so we have an urgent need to quantify the carbon dioxide that we leave behind. Next slide, please. And I want to get to the parts that we can go. Let's go on to the next one so that we can finish it fast. So this is what we do. We have capabilities at mines where we can do reaction testing, which we are doing right at the moment. We are reacting basalts. We are trying to map using either CT imaging, micro CT imaging, SEM pictures, QuemScan, FTIR, as well as NMR data to map exactly where the reactions are taking place, and at the same time do this entire experiment under pressure and temperature, as well as look at the evolved fluids. So we see what reactions are taking place. What does the resulting fluid look like? Because the resulting fluid might not be as benign as what we put in, because we might have dissolved heavy minerals, we might have dissolved materials that we really don't want to drag back up to the surface. I will stop over here because I think I'm running out of time, and we'll be glad to take questions from you. Thank you.
Thank you very much, Dr. Manika, for this insightful presentation. And we'll have 3 minutes for any question. Actually, we got some question from Isa. He said, based on the data collected from different countries, how long would you say is the average time for mineralization to be achieved on the field scale?
Right. So at the field scale, we have one example from Iceland, which is very fast, but I do not think that is an example that we can use for the world, because the conditions in Iceland are very different. It's fresh basalt, it's very porous. They have readily available fluid, which most other countries don't have. Most other countries have a shortage of water. Most other countries have basalts that are much older. Most other countries have basalts where the porosity has been greatly reduced. So getting the fluid in there is going to be a challenge. Laboratory tests, people have done tests to say the reactions take place within weeks to months. It is not hundreds of years. So in that sense, that is good news. Even in older basalts, the reactions are not that long of duration.
Thank you. And there is one more question. Where do you see the main challenges and priorities for funding research and development in this area? And how can we elevate the scale of enhanced mineralization? This is a big question, yes.
This is a big question because I think one of the places which is very straightforward is to see whether we can do some sort of beneficiation so that we produce a material that can then be used later on, so that the mineralization process gives rise to something else that is useful. And that allows us to have a value-added proposition so that the government is not subsidizing this, but it's happening as in a market-driven place. I think that is one of the big challenges for, especially for countries that have less to invest. If there can be a beneficiation process that will raise the potential, that will raise the feasibility and the appealing power of this mineralization. That's one thing. The second one is we don't have any systematic study on what types of lithologies we should be targeting. Should we be looking at any type of basalt and the porous basalts, that means those ones that have vesicles, or should we rather be going to ultramafic rocks that react more? Right? So we need and the third part is, what are we going to dissolve in addition to the mineralization that is taking place? What do those fluids look like? How much of heavy metals, of really chemicals, are we going to release, which means that the fluid that is then left over is toxic, and we have to monitor that fluid. So we change the problem into a different one, but the problem still remains of a toxic material that needs to be monitored. Right? So those are some of the burning questions I think we need to address.
I agree with you, Dr. Malika. maybe we're going to have one last question. I think he's asking about your lab, maybe. Are you able to have live injection and monitor it under CT at temperature and pressure? Okay.
Yes. So we can do live injection under pressure and temperature with the CT, with acoustic testing, and with NMR. And with, so we do seismic complex conductivity, CT imaging, and NMR T2 times measurements with live injection.
Sounds good. I think with that, thank you very much, Dr. Manika.
Thank you.
To go to our next speaker, our guest speaker, Dr. Zuhair Al-Youssef. Just let me have his slides ready. So, okay. Now we'll move to our next speaker, Dr. Zuhair Al-Youssef. Zuhair has been working with Saudi Aramco as a petroleum engineer since August 2008. The emphasis of Zuhair's work has been on CO2 storage and EOR. He is currently leading the gravity override mitigation, the gas mobility control, and CO2 sequestration research, and contributing to high-impact projects within the area of CO2 EOR and sequestration. He has authored and co-authored numbers of technical papers and filed several patent applications. Zuhair has been appointed to serve as an associated editor in the editorial board of the Journal of Geoenergy Science and Engineering, the SPE Journal, and the Journal of Petroleum Exploration and Production Technology. Zuhair received his bachelor degree in 2008 from King Fahd University of Petroleum and Minerals, his master degree in 2012 and PhD degree in 2017 from Texas A&M University, all in petroleum engineering. So Zuhair, it's over to you.
Thank you very much, Dr. Neil. First of all, I'd like to thank King Abdulaziz City for Science and Technology for the invitation to share our knowledge in the topic related to CO2 mineralization. It's my pleasure to be here today to present to you about in-situ CO2 mineralizations in basalt and the deep saline aquifer. As we are aware, sustainability is becoming increasing importantly for the global oil and gas industry. And recently, Saudi Aramco has many initiatives on sustainability in the context and framework of a circular carbon economy. So in today's presentation, I'll talk about CO2 mineralization in basalt. I'll focus mostly on the challenges when it comes to the R&D. I'm working in Saudi Aramco Upstream Advanced Research Center. So our main objective is to conduct R&D, and one of the areas that we are currently evaluating is the CO2 mineralization in basalt, as well as the deep saline aquifer. Please, next slide. So in this presentation, I'll give like a brief notes about CO2 emissions. Then quickly I'll talk about the CCS options and the main trapping mechanisms when it comes to CO2 storage and the subsurface operation. Then I'll talk about R&D challenges when it comes to CO2 mineralization and basalt and deep saline aquifers. Next, please. So first, let's put things in perspective and discuss the big picture. I'm sure you have seen this figure before or some variant of this figure. This figure shows the total CO2 emissions by world region. As you can see from this plot, the total CO2 emission now is about 35 billion tons per year. And as you can see also from this plot, the increase is dramatic, and most of this increase has happened in the past 50 years. Also, as we know, fossil fuels is the main contributor to the CO2 emissions. And also a lot of people around the world, the fossil fuels improve the life of many people around the world. So this is the reality when it comes to the fossil fuels. Currently, we are being asked to reduce our emission and to go to net zero by 2050. This is the proposed date by many, actually, which seems to be aggressive, for such a challenging task. For something that has gone up so much, how can we go down so much and so fast? Actually, that's the question of the century. Next slide, please. So here I'll talk about the circular carbon economy and the 4 Rs: reduce, reuse, recycle, and remove. The ones in green are known processes and very doable. And the ones in yellow actually are a little bit more difficult and more expensive when compared to the ones in the green. However, the ones in red are very challenging and very expensive and not easy to be implemented. Among all of these options, the biggest impact in reducing the CO2 emission by far will be from sequestering the CO2 in the subsurface formations. And those subsurface formations mainly will be saline aquifers and basalt formations. Go to the next slide, please. So when it comes to the CCS options, CO2 can be sequestered in different subsurface formations, including depleted oil and gas reservoirs, saline formation, as well as basalt formation. And since the topic of today's presentation is about mineralization, so the focus will be on saline formation and mostly the basalt formation. Next slide, please. So I'm sure everybody knows about the different trapping mechanisms when it comes to CO2 storage and the subsurface formations. There are 4 main mechanisms when it comes to the CO2 trapping mechanisms and the subsurface formation, which are: number 1, the structural stratigraphic trapping. Number 2 is capillary residual trapping. Next slide, please. Number 3, the solubility trapping mechanism, and the 4th one is the mineral trapping. Actually, I don't want to talk a lot about those all 4 mechanisms, but I'd like to list them, and the focus will be on mineral trapping because this is the main theme of today's presentation. So this happens when the CO2 reacts with different minerals at certain conditions, as Dr. Mujtaba and the Professor Barasat mentioned. So there are certain conditions at which the reaction will happen in the subsurface formation, especially in the basalt formation. CO2 will be converted to solid, so it will be trapped in the solid phase. So this is the mineral trapping. Next slide, please. So again, this figure was presented by Dr. Mujtaba, and it shows the percentage trapping contribution versus the time since CO2 injection stopped for different trapping mechanisms. The main message, as you can see from this plot, the storage security increases as we go from structural trapping to residual trapping to solubility trapping and finally mineral trapping. And as you can see, the most secured way of storing the CO2 is by converting the CO2 into solids. So in this case, the CO2 will be stored permanently in the subsurface formation. Next slide, please. So when it comes to the CO2 mineralization in basalt, what we need for this process, we need to inject carbonated water. We need to inject the CO2 and the brine together into the basalt formation at certain conditions in the presence of the reactive minerals. Dissolution will happen. After that, the pH will increase and mineralization will happen at certain conditions. So when it comes to CO2 mineralization and basalt, what are the key parameters that we need to test and investigate? These parameters include storage capacity. We must ensure that we have enough storage capacity for CO2 storage in basalt formation. Also, we have to ensure we have enough injectivity, because we have certain amount of CO2 that we need to inject. So we need to ensure that we have and we maintain actually the injectivity throughout the whole time of the project. Also, we must have the reactive minerals, and also we must have a continuous reactive minerals in the formation. So these are the main parameters that we have to investigate and to study to assess CO2 mineralization and basalt. Next slide, please. So as I said, for CO2 mineralization and basalt, we must have like the basalt, the reactive minerals, as well as the carbonated water. Dissolution will happen, pH will increase, then mineralization will take place. What are the main reactive minerals that exist in basalt? Actually, we have different minerals, but the focus will be on the plagioclase, pyroxene, and olivine. These are the main reactive minerals in basalt. So now the question, especially for us working on the R&D, we need to address many questions. We need to understand which of those different reactive minerals will impact mostly on the mineralization process. Also, which one will have higher rate of dissolution? Which one will increase the pH? Because the chemical reaction depends on the rate of dissolution, the increase in the pH, because the rate of dissolution will give us the reactive minerals, and the increase in the pH will cause or will convert the CO2 into solids. So we need to conduct more R&D when it comes to understanding which of those minerals will significantly impact, the mineralization. And this is one area actually currently we are evaluating. We are trying to understand how different reactive minerals impact the CO2 mineralization. Next slide, please. So in our lab, we are conducting many types of experiments when it comes to CO2 mineralization in basalt. We collected many samples. We did a lot of work when it comes to characterizing the samples, understanding the reactive minerals of those samples by conducting some XRD, XRF, some SEM, as well as we are doing some high pressure, high temperature exposure test in which we expose the samples to carbonated water for a certain period of time. Then we are collecting different samples from those reactors, trying to study the change in the rock mineral properties, conducting some ICP-OES measurement to understand more how mineralization will happen in basalt. And this is one area that, as I said in the previous slide, we have to focus on. How mineralization will happen, how long will it take, what are the key parameters that can impact the mineralization. And this is one area currently we are assessing and evaluating. Next slide, please. So, as Dr. Mushtaba mentioned, the water usage for such technology is really high. Talking about 20 to 30 or even 40 ton of water we need per ton of CO2. This is really huge. Maybe recycling will be one way to overcome this issue, but still we need to do a lot when it comes to the R&D. We need to find ways to minimize the water usage. Currently in our lab, we are trying to evaluate, for example, using the conventional way of like making the CO2 soluble in the brine, which is what we call it the live brine, the carbonated water. This is the conventional technique. We are trying to compare this one with the wet CO2. What do we mean by the wet CO2? We inject the CO2 into the water and then we take the CO2 out and inject it. How this will impact, the reaction? Will it cause or will it enhance or at least start the dissolution or not? Will mineralization will happen in this case or not? This is one area we are currently evaluating. Also, as we know even from this plot, you can see the solubility of the CO2 increases with lowering the concentration of the salts in the brine, with the low salinity brine. So we are currently evaluating using a new technology, which is the zero liquid discharge technology, to treat the water, the high salinity water, produce low salinity water, and then use it, for the whole process. So in this way, we can put more CO2 in the brine and minimize the usage of the brine in such case. So this is one of the areas we are currently evaluating when it comes to the R&D. So water usage is one of the key areas that needs to be investigated, and I think we should encourage the R&D and we should support R&D to come up with a solution to minimize the water usage and for making the technology very feasible in the future. Next slide, please. Also, when it comes to the other parameters related to the R&D, injectivity enhancement. As we know, after injecting the CO2 in the basalt formation, there will be some mineralization. So this will cause plugging inside the formation. So we need to find solution for this because we need to maintain certain injectivity. So we need to do a lot when it comes to the injectivity enhancement. Stimulation jobs will be like, this is the conventional way, but we need to find some innovative ways for injectivity enhancement when it comes to CO2 mineralization and basalt. Also mineralization, we need to ensure the continuity of the reactive minerals inside the formation. How to come up with the continuity or answer the question, is this formation contain continuous reactive minerals or not? This is one area that we have to investigate. How long will it take for mineralization to happen? We need to understand this. Modeling, we need to build our capability, when it comes to modeling. I think Professor Barsad mentioned about some work when it comes to the reactive transport modeling, and this is one area that we should focus on and encourage the research in such topic. Also, during the injection of the CO2 into basalt formation, there will be some dissolution. Rock petrophysical properties will change. So we need to understand the formation stability by conducting rock mechanical strength testing. So this is one area still we have to assess when it comes to CO2 mineralization in basalt. So these are some of the areas that we have to investigate. And currently we are in our R&D, in our research center, trying to address some of those challenges related to CO2 mineralization in basalt. Next slide, please.
Doctor, we just have 1 minute to...
Okay, I'll do the next slide quickly. So when it comes to CO2 mineralization and saline aquifer, this is one area. The focus actually was on CO2 mineralization and basalt, but the question, is it possible to do mineralization and saline aquifer as well? Because by converting the CO2 into salt will increase the security of the project, and if we can do it in saline aquifer, this will be really great. Next slide, please. So actually in our lab, we did some experiment in which we used some carbonate samples and we added some salt and some accelerator to the solution. We injected the CO2 and then we tested the mineralization in saline aquifer, and we found that the mineralization of CO2 in saline aquifer is possible. We collected some samples. We did some ICP-OAS measurement. We did some core flood. We assessed the pressure drop. I don't want to discuss it in details, but is it possible? Yes, it is possible, but still we need to do a lot of investigation when it comes to CO2 mineralization and saline aquifer. Next slide. So in conclusion, CO2 sequestration represents one of the largest potential carbon intensity reducer technique. Saline aquifer and basalt are two options when it comes to CO2 sequestration and subsurface formation. To accelerate the mineralization, basalt formation is one of the candidates. Major challenges when it comes to CO2 mineralization and basalt, the amount of water needed for this process, injectivity, and also we have to ensure we have continuous reactive minerals present in the formation. R&D needs to be conducted to fully understand the mineralization and basalt formation. Accelerating CO2 mineralization and saline aquifer is possible through the injection of some chemicals. This area still needs to be further investigated. Thank you very much for listening.
Thank you very much. Thank you very much for your presentation. And now we'll take one question. So because we ran out of time. So one question from the audience. They said the zero liquid technology. This is a question from Isa Muhammad. The zero liquid technology for low salinity fluid production, does it produce wastewater rich in ketones? Could you shed light on the possible concentration of ketones in the wastewater after the low salinity fluid production?
Actually, this technology, it's being already tested here in Saudi Arabia, in some of the Saudi Aramco fields, in which they took the produced water, because usually the produced water has a lot of contaminants. So they collected this brine, okay, and then they treated this brine with the zero liquid discharge technology. They removed almost all the hydrocarbon from the brine, as well as most of the salts in the brine, and we ended up with brine with very low salinity, less than 1,000 ppm. When compared to for example, when we compare it with the high salinity water like seawater is around 60,000 ppm. So, and usually the produced water from the formation, even in some cases, it's more than 100,000 ppm. The technology was able to reduce the salinity to a very low concentration of the salt, less than 5,000, even 1,000 ppm. So yeah, this is when it comes to the ZLD technology that's being recently tested by Saudi Aramco.
Thank you very much, Dr. Zahir. And now we will go to our next speaker, Dr. Hatem Al-Hazmi. Dr. Hatem Al-Hazmi is an associate research professor at the Institute of Carbon Management Technology at King Abdulaziz City for Science and Technology, specializing in life cycle assessment within carbon management. With 18 years of experience, he has helped promote sustainable practices across both private and governmental sectors through the application of LCA. Dr. Al-Hazmi integrates the principles of the circular economy with the LCA to advance national energy strategies, improve resource efficiency, and enhance decision-making for sustainability across various sectors. His high-impact journal publications significantly contribute to the field. With that, Dr. Hatem, the floor is yours.
Thank you, Dr. Naif, and I'm honored to present our work on life cycle assessment for In-situ mineralization, a pathway to sustainability. A little background about the subject. According to IPCC, significant volume of carbon dioxide must be removed from the atmosphere for the world to achieve its climate goals. One of the promising approach is carbon dioxide removal, which involve a set of techniques aimed to remove the CO2 from atmosphere and sequestering it to prevent re-entry into the atmosphere. One of the carbon dioxide removal approaches is the carbon mineralization, which is a natural process where CO2 reacts with minerals to form stable solid carbonated minerals. This process can be harnessed to permanently remove CO2 from atmosphere. If it's done naturally, some of its strength, it's effective, it's permanent, there is no energy required, and it's cost effective. Next slide, please. For in-situ carbon mineralization, it focuses on injecting the CO2 into mafic and ultramafic rocks, where it reacts to form solid carbonates, effectively locking CO2 in a stable form. The objective is to ensure the amount of CO2 stored or removed is greater than the project emission, and any CO2 releases from the storage site. How we can measure this? The life cycle assessment technique or methodology can play a huge role in measuring this. Next slide, please. First, let's define the life cycle assessment, or LCA, which is a technique used to evaluate the environmental impact of a product, process, or surface for raw material acquisition through product use, through the production and use and end-of-life treatment. LCA helps make informed decision to improve sustainability by providing a comprehensive view of environmental impact. By analyzing the entire life cycle, LCA provide a comprehensive view of environmental impact, ensuring informed decision to improve the sustainability of product, process, and services. Some of the key points that the LCA can highlight, it's identify and quantify environmental burdens, evaluate potential environmental impacts, understand the opportunity for improvement. The LCA works under the principle of a framework of the ISO standard 14040 and 14044 to ensure that its consistent and internationally recognized approach to conduct LCA study, providing credibility and reliability to the assessment process. We can see from the LCA steps, it has 4 steps. The first one, goal and scope. The second one, it's the inventory analysis. The third one is impact assessment. And the last one is the interpretation. For the goal, the initial step involved clearly defining the purpose and the objective of the LCA study, including the reasons for conducting it, the intended audience, and the decision that will be supported by the result. It also established the system boundary and the function unit. The function unit, which is quantifying description of the service provided by the system under the study. In our case here for the carbon mineralization, the function unit can be 1 ton of CO2 stored. Inventory analysis, which is a step involved collecting data on all the input, such as the raw material, energy, and the output, like the emission, the waste associated with the process. Second slide, please. And we can go to the third step, which is the impact assessment. In this step, the environmental impact of the input and the output identified in the inventory analysis are evaluated. This involves characterizing and quantifying the potential environmental impact, such as global warming potential, water use, and resources depletion, to understand the broader implication of the system. This system helps translate the inventory data into environmental impact indicator. The last step, which is the interpretation, it's the final one, which is involve analyzing the result from the inventory analysis and impact assessment to draw meaningful conclusion and make recommendation. This step identified the significant environmental issue, assess the finding, and suggest improvement. The interpretation phase ensure the LCA results are understandable and useful for the decision making, and the communicating finding to stakeholder. Next slide, please. Here we can see that LCA has iterative nature, which is the more it is very data intensive. So we can start by screening LCA, which is contain of secondary data, and just to provide a preliminary overview of the potential environmental impact. And maybe after that, we can do a full LCA for internal benchmarking, which involve collecting primary data for key process and more specific process data. This aims to internal performance improvement and benchmarking. The more time consuming, which is the full LCA for competitive claim. In our case, if for a specific technology, it's required better data for key process and flow, include uncertainty analysis and the ISO review. Usually it is used for making competitive claim and ensuring compliance with standard. Next slide, please. Here, first, we defined the physical boundary. This is a picture being taken by the project CARFOX for the in-situ carbon mineralization. We can see the physical boundary is interface with the CO2 transportation, in which the CO2 is offloaded to the CO2 geological storage facility. Then the geological injection facility and the injection well. And we have to include in this all the items being used in the project. Then if you go to next slide, please. Here we are drawing the system boundary for physical and the emission for the project, which is include electricity, the input and the output in terms of energy, water, and the output from the construction phase or from the drilling or from all the process being used in our system. Next slide, please. For the result from the LCA, we can see that we can have a potential finding, which is came from as efficiency of the carbon sequestration or energy use or environmental trade-off. Next slide, please. And sometimes we can use it as the potential uses, like understanding the system, which can provide through understanding of the assist mineralization system from life cycle to perspective, and process optimization, which help optimize the process to improve the assist mineralization system and enhance the net reduction of CO2. Next slide, please. LCA came with its limitation. Despite its benefit, applying LCA to in-situ carbon mineralization faces several challenges. Technical challenge like data availability and quality can be major obstacle to performing full-scale LCA. Economic challenge, conducting comprehensive LCA study can be costly with uncertainty regarding long-term economic benefit. Methodological challenge, the variability in LCA method and assumption can affect the result, making it difficult to accurately capture all environmental impact. Addressing these challenges is crucial for improving the reliability and the usefulness of LCA in assessing new technology, such as in-situ carbon mineralization. Next slide, please. The recommendation it's to improve the effectiveness of LCA in carbon mineralization. The first one is the methodological harmonization, which can happen by increased transparency and harmonize LCA approach through collaboratively developed guidelines and best practice. improve data quality, address data gap, and improve data access to support robust and trustworthy LCA study. Then develop a global data sharing, establish a global data sharing hub with open source tool and publicly available data set to improve global capacity for comprehensive LCA. Considering scale-up impact, expand the boundary of LCA, include the environmental and economical impact of scaling up carbon dioxide removal technology, including the carbon mineralization in-situ technique. Considering increased competition for resources like raw material, land, and water. Implementation of these recommendations will help maximize the benefit of LCA for carbon mineralization and contribute to more sustainable practice. Next slide, please. LCA can come with big opportunities. For example, improved confidence, LCA provide detailed impact result throughout the life cycle of in-situ carbon mineralization and other carbon dioxide removal technologies. These transparent and comprehensive result enhance social and market trust, leading to increase and sustain investment. This financial support is crucial for helping this emerging technology to reach maturity and become commercially available. Technological innovation, advancement in carbon capture and storage technology, along with improved method for monitoring CO2 sequestration and mineralization. Policy and regulation, supportive policies and incentives of carbon capture projects combined with the standardization of specific LCA methodology. Research and collaboration, ongoing research and collaboration between industry, academia, and government to drive continuous improvement and enhance availability of data. Global data sharing, facilitating access to high quality data and tool to support comprehensive LCA study and harmonized methodology worldwide. Next slide, please.
1 minute, Doctor.
Yeah, I'm trying to be fast. We conclude with carbon mineralization in-situ is a promising technology for reducing CO2 level. LCA provides comprehensive framework to assess optimization, environmental impact. Integrating LCA into carbon mineralization project can significantly contribute to achieving global climate goals. Continued research, collaboration, and best practice, which promote transparency, improving data quality, and considering scale-up impact, are essential for advancing these technology and ensuring they align with the broader sustainability object. Thank you for your attention, and I'm happy to answer any question you may have. Thank you.
Thank you very much, Dr. Hatem, for your great presentation. Actually, we're going to have just one question. And since you are mentioned that LCA is an intensive data collection, I would like to ask you to how can the international collaboration play an effective role in promoting and accelerating the adopting of carbon mineralization technology across different countries? I am here emphasize the international collaboration.
Thank you, Dr. Naif. It's very important question. Actually, international collaboration in life cycle assessment context for carbon mineralization can promote to standardize the LCA methodology and it could be happen by enhanced data sharing and leverage shared research and development by harmonizing the methodology and policies and pooling financial and technical resource and conducting joint pilot projects. I believe country can collectively accelerate the adoption and implementation of this technology, which will ensure the global sustainability and effective common practice.
Thank you very much, Dr. Hatem. And I would like to thank you all. Before we closing this session, I would like to share with you some key messages. It's really a rich session, so we have a lot of things that we had during this session. As we conclude this webinar on carbon mineralization technology, I'd like to take a moment to reflect on the key points we have discussed during the session and the path forward. Our goal, as outlined by the carbon dioxide removal, the CDR mission, is ambitious but crucial. It's to enable CDR technologies to achieve a net reduction of 100 million tons of CO2 per year by 2030. This goal underscores the importance of our work and the urgency with which we must advance. Throughout today's discussion, we've delved deeply into the science and potential of CO2 mineralization in geological formation, especially in basalt rock. Injecting CO2 into basalt formation has been highlighted as a promising method to accelerate mineralization. However, this approach is not without its challenges. Key issues include the substantial amount of water required, the injectivity rates, and the assurance of effective mineralization. These factors are critical and must be addressed to optimize the process. Several critical aspects must be carefully evaluated to assess the feasibility of in-situ carbon mineralization. These include geological suitability, efficiency of the mineralization process, and the long-term stability of the stored CO2. Conducting pilot tests is crucial in advancing our understanding of the in-situ carbon mineralization, especially in basalt rock. These tests will provide valuable data and insight, helping us to refine our methods and technology. In-situ carbon mineralization offers significant benefits by converting CO2 into stable minerals for permanent storage. However, applying LCA faces several challenges, as discussed in the last presentation, which is technical challenges, the data availability and quality, economic challenges. LCA study can be costly. However, because we have a lot of uncertain long-term economic benefits, methodological challenges, and we have to address all these challenges to improving the LCA reliability and usefulness. However, the journey toward large-scale deployment of these technologies is really have a lot of challenges. Securing fund for large-scale testing site, supporting a lot of research, and exploring innovation applications such as different type of electromagnetic surveys in mine tailing and critical priorities, as mentioned before. The value proposition of carbon mineralization extends beyond mere CO2 reduction. It offers potential benefits in industrial processes. These innovations can drive economic growth while contributing to our environmental goal. In conclusion, the path to achieving the CDR mission is clear but demanding. It required concerted efforts from researchers, industry, policymaker, communities, together with innovation, collaboration, and unwavering commitment, we can make significant action toward a sustainable and carbon neutral future. As we wrap up, I want to thank each of our speakers for their valuable contributions and all of you for attending and participating in today's webinar. We hope you found the session informative and engaging. Don't forget to check your email for the recording or any additional resource that we will be sending out. Have a great rest of your day, and we look forward to seeing you at our next event in future. Thank you very much. Thank you all.
شكرا لكم جميعا.